Hello everyone and welcome to Physics 213, University Physics 2. And with the textbook that we're using, which is the Halliday-Resnick, our material for this course is going to start in Chapter 21, and we will continue through Chapter 30. And this course material is broken up into basically three different segments for chapters 21 through 24. We are going to discuss things like electric field and electric potential. So electric field and electric potential. And once we have the foundations of those two topics under our belt, we will make our way into the second segment of the course, chapters 25 through 27, which primarily deal with circuits. And we're going to limit ourselves to mainly capacitors and resistors for this course material. It's not until we get past chapter 30 that we can actually start incorporating things like inductor coils or solenoids into our circuits. That's not to say that you can't continue reading through the text material, because you will have access to the full text regardless of whether you have a physical text or an e-text, because the Wiley Plus software that we use for this course allows you access to the full text material. And then for chapters 28 through 30, we're going to be dealing with the effects of magnetic fields and magnetism, magnetic force, and how the magnetic field and the electric field essentially are two sides of the same coin. And so with that said, we'll go ahead and start the material for our course. And if anyone has ever taken a class with me before, I typically start with the same question that the book poses at the beginning of every chapter. And that question is, what is physics? And this question, as it's asked at the beginning of every chapter in the book then takes that idea and presents some kind of phenomenon or problem or issue, which can then be answered using the material from that specific chapter. But what I like to do is generalize this question a bit more. Instead of saying, what is physics? I'm going to ask, what is the universe? And that might sound even more complex, but the universe is really only going to be made up of two things. And those two things, arguably, are going to be matter. And yes, I realize that there's regular matter, there's antimatter, dark matter, but we're gonna go ahead and squeeze all of that into this one category. And then the other thing is energy. And likewise, there is a theory behind something called dark energy. In some advanced physics courses, you can have negative energy, but again, we're going to clump all of that together into that one category. So the entire universe, we have two things that we can basically study. We can study matter, or we can study energy. And if you want to study matter and how matter interacts with other forms of matter, then you take a chemistry class. If you want to study energy and how energy can be released, transferred, transformed, how we can use energy for things like chemical reactions. Then you take a physics class. And then, after you've taken a bit of chemistry and you've taken a bit of physics, we combine the two using mathematics as the universal language. And you have the ability to now study everything else. So any other kind of science or engineering class is going to be some combination of physics and chemistry along with some mathematics. And so this is why everyone, regardless of their program of study, has to take a certain amount of physics, a certain amount of chemistry, and a whole lot of math, because these are the foundation courses that allow us to explore all those other topics. So all those other sciences, all those other engineering topics, they are a combination of those three classes: chemistry, physics, and math. And the more you dig into one particular subject material, or the more advanced those classes that you take, you start to see that even these two subjects are not completely independent of one another. In fact, there were quite a few graduate courses in physics that I took that required an intense amount of chemistry knowledge, and vice versa. So even the two are not completely separate of one another. So with that in mind, we're going to again focus on the physics as much as we can. Every now and then we might have to sneak in a little bit of chemistry, but we'll do our best to limit things to physics for this physics course. And in Physics 1, in Physics 211, almost everything that we studied was on the macroscopic scale, and macro meaning large. And so all of the kinematics, the force relationships, the energy, the momentum, all of that had to deal with masses that were on a fairly large scale. And when we say large scale, what we mean is large in comparison to things like particles. And a particle could be anything from an atom to a molecule, maybe even a speck of dust or a grain of sand. So these are going to be very, very small objects, and as such they're going to have very, very small amounts of mass, whereas in the macroscopic scale you had large masses. And so, as we said, in comparison, these large masses versus these small masses, these are really what are going to distinguish the two classes. Because when we have large masses, the physics of the system are going to behave in such a way that primarily forces like gravity are going to have the greatest influence. Whereas when we have very small masses, well, gravity in and of itself depends on mass. We could represent the force of gravity in a system as mg, where m was the mass and gravity was the acceleration due to gravity. And then the force of gravity would be decided by how much mass the object had. We could take that same expression and generalize it to look something like this. And you should recognize this. This is Newton's universal law of gravity. And this describes the same gravity force, but in a more generic presentation, because this equation right here is only valid when we're on the surface of the Earth. And so if I wanted to know what the effects of gravity were on the Moon or Mars or Jupiter, I couldn't use this expression, because this expression is assuming that we're using the value of gravity on the surface of the Earth, whereas this expression can be used anywhere between any two masses. So mass 1 and mass 2 would be the two masses involved in the situation. But now consider that you have an incredibly small mass, like an atom, or it could be something even smaller than an atom. We have elementary particles like electrons. We have composite materials like protons and neutrons. These particles have extremely small masses, and if we were to try and plug those particles in to the gravity expression, we would get a negligible amount of force. And so forces like gravity are not really going to play a part in a lot of the particle-to-particle interactions that we see. And so what we need to do is we need to consider other types of forces that are out there. And when it comes to types of forces, there are 4 categories. There are 4 types of forces out there in the universe, and we're not talking about the forces that we learned back in Physics 1. Obviously, gravity will be one of those. But then the other types of forces that we had back in Physics 1 were forces like tension, normal force, friction force, centripetal force. All of those forces are going to fall into one of the categories that we're going to list here today. And so those 4 forces, which include gravity, the first one is going to be the strong nuclear force. And this is the force that is responsible for holding together the nucleus of atoms. And we'll talk about that a little bit more in a moment. But this force is only present and only operates within the nucleus of the atom. And so outside of the atom, we don't see the effects of this force as such. As long as we're outside of the nucleus of an atom, we're really not going to encounter this kind of force. But as it turns out, of all of the forces, this actually ends up being the strongest of all of them. The only problem is that it's so localized at the center of the atom, at the nucleus, that we almost never encounter it anywhere in our day-to-day experiences. The second force is what we're going to call the weak nuclear force. Now, the name itself, weak, does not imply a strength relationship here. It's still a force that operates within the nucleus, but we've just named it weak because that correlates to strong. The weak force is a little bit weaker than the strong force, but where these strong forces deal with holding together sorry, I had that spelled wrong. So holding the nucleus together, the weak nuclear force actually deals with a phenomenon known as beta decay. And this is where a neutron inside of the nucleus of your atom will decay into a proton and an electron. And the proton will usually stay inside the nucleus, but the electron will escape. And so the name beta decay refers to the generation of these electrons that then exit the nucleus. And now is where we have to switch over to chemistry for a moment. If we have a neutron inside of a nucleus, so in here we may have a number of protons and neutrons. If one of those neutrons all of a sudden loses one of its electrons, it will turn, I'll go ahead and color in the protons that we have here. It will then turn that neutron into a proton. And so that changes the proton count inside the nucleus of this atom. And as we know from chemistry, the identification of any atom is based on the number of protons, or the proton count. And so this nuclear decay process, this is one way of seeing an element actually transform itself from one type of atom to another. But again, this is something that occurs inside of the nucleus of the atom, and so it's not really something that we're going to run into in this class, because these two forces, the strong and weak nuclear forces, are forces that are better suited for a course in nuclear physics. So this would be an entire semester, if not more, completely devoted to the interactions that occur inside the nucleus of an atom. We want to remain outside the nucleus. Trust me, there's still plenty going on outside the nucleus of an atom. And so that brings us to our third force, which is the electromagnetic force. Now some books will break this up into two separate forces, and so some books might even say that there are 5 forces out in the universe. But the electromagnetic force, as I mentioned before, these are basically 2 sides of the same coin. And these forces relate primarily to the charge of the particle. I don't want to say the charge of the object, because as we're going to see here later in the video, the larger the object becomes, the more difficult it is to relate back to the charge of the system. And that I'll clarify that statement here in a little bit. Well, what I mean by charge is electric charge, and we will define this here in a moment. I just want to finish off the list here, because the Fourth and final and weakest of all of the charges is gravity. And so this relates to the mass of the object itself. And how it relates to the mass of the object, that's right there. We know that if we have two or more masses in a system, those masses will interact based on the force of gravity. But given this list, we've literally gone from strongest to weakest in this list. And all of last semester, or at least all of Physics 1, was primarily focused on forces like gravity. And now we're told that there are other forces that are even stronger. And if you have forces that are stronger, then why are we seeing so much of our universe moving around based on the ideas of gravity? Why are we not seeing more influence from these forces? And the answer for the first two, we've already covered that. These two forces are occurring inside the nucleus of the atom. And so we don't really see the effects of these forces outside of the nucleus of the atom. But this right here, the electromagnetic force, does occur outside of the nucleus of the atom. And yet we're saying that this is stronger than gravity. So how can that be? Well, we need to take a look at the idea of electric charge, and once we get a better definition of electric charge, then we'll actually see why the electromagnetic case is going to be stronger than the gravity case. So, electric charge. The definition of electric charge, my definition might be a little bit different from the books, but basically the definition of charge is that it is an intrinsic property of the material which is identical to all other, and actually I need to make a revision already. I don't want to say of the material, I want to say of the particle. Because materials are going to be made up of collections of particles. So this is an intrinsic property of the particle, singular, there we go, which is identical to all other particles of that type. So what does that mean? Well, let's talk about some particles that we know. We already mentioned up above that there were particles like protons, electrons, neutrons. So let's just go ahead and list those. A proton is a type of particle. An electron is a type of particle. A neutron is a type of particle. There are plenty of other particles that are out there. One of the big types of particles that you would run into with nuclear physics would be things like quarks. But quarks, even though they're a form of elementary particle, what we found out is that they actually have a fractional amount of charge, and they can't actually exist on their own. They have to combine to form some kind of larger composite material. And so we're going to exclude the discussion of quarks from this class. Those would be more appropriate in a nuclear and particle physics course. So everything that we're going to have here is going to be a particle which has some integer value of charge. And so the proton is going to have a symbol of P, and protons carry what are known as positive charges. And so we're going to go ahead and put a positive in the upper right hand corner. The electron, we will use the symbol of E, and the electrons have negative charges. And just like with positive and negative numbers, the positive and negative charges are going to indicate the difference between the positive and negative signage. The neutron will have a symbol of lowercase n, but the prefix of neutron, nu, stands for neutral. And what this means is that we do not have an electric charge on the neutron. And so I'm not going to put any kind of symbol in the upper right hand corner. If you absolutely had to, my recommendation would be a 0. But N0 or NO spells no, so no charge. But most books are not going to have that superscript in the upper right hand corner. So a proton has positive charge, an electron has negative charge, a neutron has no charge. The next question would be if the proton has positive charge, and if we're treating the plus minus signs like numbers on a number line, is there a certain amount of charge associated with these particles? And the answer is yes. It turns out that electric charge is quantized. So what does that mean? Well, the term quantized has the root of quant or quantity, and what that means is that you have a specific amount. So each charge will have a specific amount, and given the definition of electric charge, the particle, given the specific amount of charge, has to have the same amount of charge regardless of that type of particle. So really what all of this definition means is that every proton in the universe, so every particle of the same type, has to have the same amount of charge. So every proton in the universe has to have a charge of positive 1 quantity. Because whether we realize it or not at this point, we say P positive for the proton, but positive what? Well, positive 1. Our proton is going to have a positive 1 electric charge. Our electron will have negative 1 electric charge. And just in case you were wondering, when we were talking about the beta decay phenomenon, where we said a neutron inside of the nucleus will break up to form a proton and an electron, well, that neutron had 0 electric charge, and all of a sudden it broke itself up to produce a proton which has a positive 1 charge and an electron which has a negative 1 charge. While that is a true statement, +1 and -1 make 0, but this helps us to sort of justify how the proton and the electron can have equal and opposite charge values. And so now we actually need a value. We need to know what is the quantity of that electric charge. And we are going to call this the elementary charge value. So this is the smallest amount of charge that we can have on a particle. Again, we are not considering quarks. Quarks cannot exist in nature by themselves as far as we know. They have to be paired up with other types of quarks. But this elementary charge value, we're going to shorthand this to call it 1e. So 1e is 1 elementary charge. And the value of that elementary charge is 1.602 times 10 to the negative 19 coulombs. So our unit of charge is a coulomb, capital C for short. A lot of students just see C and they think charge, but C is actually a coulomb. And Coulomb was the individual that actually figured out a lot of the charge-to-charge interaction, or at least the math that we're going to put behind this. And so now if we come back over to our list of particles, our proton has a positive 1 charge, and so that means that we would have positive 1 elementary charges associated with that proton. And I'm going to get rid of this stuff here so I have a little bit more room to write, which is equal to positive 1.602 10 to the minus 19 coulombs. Now here's where things might get a little confusing, because we are now using E to represent the electron, but now we're also using E to represent the elementary charge. Well, the electron has a negative 1 elementary charge. We know that because the number that we have up in the right hand corner, that is going to describe the integer value of electric charges associated with that particle. So our electron has a negative 1 elementary charge, negative 1.602 10 to the minus 19 coulombs. The neutron has 0 elementary charges, or 0 coulombs. Now there are other particles out there. One good example for this kind of discussion might be a positron. Oh, I spelled that wrong. Trying to talk and write at the same time. My brain can't do that. There we go. Positron. All right. Well, for anyone that doesn't know what a positron is the antimatter equivalent of an electron. And so when it comes to antimatter particles, with antimatter particles, your particles will have the same mass but opposite charge. So if a proton is the anti-version of an electron, that means we would have an electron of positive charge, or positive 1 elementary charges. Now, in labeling the positron, we've essentially gone down the list just using the first letter as the initial for the particle. Now, we don't want to make the mistake of calling a positron P plus 1, because we're already using that as the label of a proton. Now, both the positron and the proton have the same charge value of positive 1 elementary charges, but the masses are very, very different. Electrons are going to have much, much smaller mass than a proton, and so we're not actually going to call the positron P plus 1. We're actually going to go ahead and adopt the notation that we had right down here. So this is an electron with a positive charge, and so that tells anyone that's looking at it, oh, it's a positive charge, we've got E for electron, that's a positron. But just as we had written below, this is a positive 1 elementary charge, so we have positive 1.6, 10 to the minus 19, and coulombs. Another particle, one that's pretty popular here at the School of Mines and in the Black Hills territory, is the neutrino. And there are different ways that I've seen the neutrino, or at least different symbols that I've seen given the neutrino, but sort of an italicized N is one version. But just like the neutron, the neutrino has the prefix of nu, which indicates that this particle, neutrino, has a charge of 0. And so, just like the neutron, I'm not going to place any kind of superscript or number up above, because our neutrino has 0 elementary charges associated with it, and so 0 coulombs. Now, the neutrino is another particle that results from nuclear reactions. It falls into the same category of particles as the electron, but it does not carry any charge with it. And there are different types of neutrinos that have different mass values. But those neutrinos, as they travel through space, and these are phenomena that we're still studying and trying to figure out, but these neutrinos can actually oscillate from one type of neutrino to another. They can actually change their form and charge as they travel through space, and we're still trying to figure out how they do that, because to change a charge and to change a mass is technically not possible, and so we're doing quite a bit of research to figure out how that happens. And that research is continuing at the Sanford lab with the DUNE project, Deep Underground Neutrino Experiment. All right, so we have a pretty good list of particles here. The last one that I'm going to put on here is an alpha particle. And an alpha particle, this is another particle that can be produced through nuclear decay. But this is basically a helium ion. And so your helium by itself, if we were to draw a helium atom, helium is defined as having 2 protons, so 2p plus 2 neutrons. And then in order to make the atom itself neutral in terms of charge, we have 2 electrons that are orbiting around the nucleus of our helium atom. And so this helium atom has a net charge of 0. If we were to add up all of the charges, we have 2 positive elementary charges in the form of the 2 protons. We have 2 negative elementary charges in the form of the electrons, and so we get a net charge of 0. But now if we were to strip away the 2 electrons, so now all we have left is basically the helium nucleus. Without the 2 electrons orbiting around that nucleus, we now have a net charge of positive 2 for this particle. This entire construct is what we're going to call our particle. And so technically this would be a helium ion, and we would label it as such, as He positive 2, or I've even seen some chemistry books that'll write it this way. We'll do 2 positive. But what this does is it tells us that we have a helium nucleus with a positive 2 electric charge. And from there, we basically have the groundwork for all of chemistry, because chemistry is all about producing some kind of bond between the atoms, and those bonds are going to occur based on either the attraction or repulsion of the charge of the particles. And so now is where we're going to figure out how electric and magnetic charges can be so much stronger than gravity almost said gravity charges, but gravity forces. So the idea behind electric charge is what is going to basically tip the scales between electric force and gravity force. We'll talk more about magnetic force when we get to the magnetic section of the course, which is at the end of the semester. So now what we need to do is we need to figure out, well, if I have 2 particles with some charges, how are they going to interact with each other if we can't use gravity? Because gravity, like we said, these masses are just way too small that we're not going to register really any kind of effect from gravity. And so Coulomb, the person that we have our charge named after, Coulomb thought, well, these charged particles, they're still going to interact with each other. So I'm gonna draw 2 particles here, and we need a way of designating the individual charges of each particle. Now it might make sense to use the letter C for charge, but we're actually going to use the letter C later on in the book to designate capacitance, and so I need something else as a label for charge. Well, we already said that charge was going to be quantized. Where did I have that? I think I erased it. But we said that charge was quantized. And the elementary charge was the smallest individual amount of charge that we could have. And so any other charge value would have to technically be some integer value of the elementary charge. So n is some integer value of E, the elementary charge. And so those specific quantities, I'm going to go ahead and, well, I'll just steal the letter Q for quantity. So we're going to use Q to designate the electric charge of a given particle. And this will not be restricted just to individual particles. We will eventually make our way back to the macroscopic scale. We will eventually start putting these charged particles together to build larger and larger constructs, and then we need to see how that combination of charges will affect the physics in the system. So moving on back to our two-particle system of two charges. Our first particle will have charge Q1. Our second particle will have charge of Q2. Now, if these two particles had a sizable amount of mass, we'll just go ahead and label each of these with some masses. If these particles had some pretty considerable mass, then we would be able to measure some kind of gravity force between the two charges using Newton's approach. So mass 1 and mass 2 are the two masses respectively. G was the universal gravity constant, and R was the center-to-center separation distance between the two masses. And the reason that needed to be a center-to-center separation was because when Newton came up with this equation, he was primarily looking at things like moons and planets, things that were in relatively close proximity to each other with respect to their individual radii, and so we had to use the center-to-center separation. And Coulomb looked at this and said, well, is there a way that we could rewrite this expression not for mass but for charges? One thing that Coulomb found was that the more charge a given particle had, the more of a force relationship that would be registered. And so we're going to call this our electric force. And the first thing that Coulomb noticed was that the more force, the more charge, and vice versa. So these two particles, they each have their own charge, but if we end up with particles with more charges on them, the magnitude of force will increase. Coulomb also found that the separation distance between the charges followed the same inverse squares relationship. Now, technically, we should still call R the center-to-center separation distance. But when you're dealing with particles which are already so small, let's say that these two particles were both protons, and these protons are 10 centimeters apart. Well, how much does the radius of an individual proton compare to the separation distance that we're measuring of 10 centimeters. It's going to be minuscule at the most. And so what we can do is we can just kind of fudge this as being the surface-to-surface separation between the particles. At least until these objects start getting closer to the macroscopic scale. Well, this is looking very, very much like Newton's version of his gravity equation. The only thing that we're missing here is that proportionality constant. For Newton, he had big G, and the way Newton found the value of big G was Newton just took the ratio of everything else that was in the expression to find big G. And as it turned out, big G was a universal constant. This number kept showing up again and again and again, regardless of the mass combinations, force and separation distance. And so Coulomb kind of played off of that idea and said, well, what would happen if I took the electric force that was being measured, and we formed a ratio of that against everything else that was in the expression. And for that, we get another universal constant. We got another proportionality constant. This one is our lowercase k value, but this comes out to be approximately 8.89 times 10 to the 9th. And then, well, we need some units here. How are we going to get the units? Well, we could go through what we have for units already in the expression. We have force, which is in newtons. We have the product of two charges. Well, charge is coulombs, so that needs to be coulombs squared. And then we're dividing by r squared within the denominator, so that's actually going to flip up to the top. But our radius, or our distance value, is going to be measured in meters, so that is meters squared. And so this is our proportionality constant. This is the value that we're going to be using time and time again as we try to figure out the force that is interacting between these two charged particles. And now is where we can actually prove to ourselves which of the two forces is going to be stronger. So two protons. This is what we decided our system of particles was going to consist of. Two protons. And given the mass and charge relationships, which one is stronger? The gravity force or the electric force? Well, we said that these two protons were going to be 10 centimeters apart, so we can go ahead and put 10 centimeters into the denominator. 10 centimeters is going to be 0.1, so we'll square that. 0.1 squared. Our k value, as we mentioned, was 8.99 10 to the 9th. We're going to have two protons, which will each have the same charge of positive 1 elementary charges. So we can put that in there. And I'll need to make myself a little bit of extra room there. 1.602 10 to the minus 19 quantity squared. So there's the electric force that is present between the two protons. Now we can go ahead and crunch those numbers, but we still need to finish off the gravity equation. I neglected to write out the value of big G, but I'll put that in here now. The value of big G was 6.67 10 to the negative 11. And then since we have two protons, they're both of the same mass, we can just write that as m squared. And then we need to look up the mass of a proton, which is, and I'm looking this up on my phone at present, but we have approximately 1.67 times 10 to the negative 27 kilograms. So we're looking at which one of these quantities is going to be stronger. And right away I can tell that it's going to be my electric force because of all of the power notations within the numerator. Let's see, I'm going to get a power in the numerator that is approximately, well, I won't do approximate. I'll put this into my calculator. So in the numerator we've got approximately 10 to the negative 29, and I'm not including what I have in the denominator yet, but this would be over 10 to the negative 2, which would be approximately 10 to the negative 31. Again, we'd still have to go through with all the actual arithmetic here, but this is approximately the magnitude of force that we would get between the two protons based on their charge, whereas we would get and again I'm putting these numbers we would get approximately 10 to the negative 65 newtons of force just by relying on gravity. So in comparison, how does a force of 10 to the negative 65 compare to a force of 10 to the negative 31? And obviously this one is far, far greater by more than 30 orders of magnitude. Now I realize that they are both considerably small, so small that we would never register them ourselves, but we need to consider the types of particles that these forces are acting on. We're talking about particles that have masses that are 10 to the negative 27. And so these forces would actually be quite considerable compared to the mass of the particles. But we now see that the electromagnetic force is far greater than anything that gravity could ever possibly perform. And so when we are at these microscopic levels of particles with charges, the electric forces are going to be far more influential than anything that gravity can do. And so for the time being, what we are going to do is we are essentially going to ignore any of the effects of gravity on these individual particles. The only time that we're really going to need gravity is if we happen to see the mass of the object show up. Now what we have, and this is kind of the ultimate goal of today's discussion, is something called Coulomb's law. So Coulomb came up with this expression to define the magnitude of force that exists between two charges. And as you can see, that force equation does not involve the mass of the particle. The only time that we would actually need to incorporate the mass of the particle is if we wanted to know how fast that particle was accelerating due to the force itself. Now that is a completely different physics problem. Obviously we could go back to physics 1, review some of the stuff that we have on force, mass, acceleration, kinematics, etc. But for right now, this is going to be the end result of today's video. When we come back for part 2, we'll actually take that equation and we'll start applying it to different systems of particles. Because for right now, if you notice, there's only room in that equation for 2 charged particles. What are we going to do if we have 3 or 4 or 1,000 particles? How are we going to get an electric force in that case? So something to think about. But until then, I'll see you at video 2.